All right, this is our last activity in this unit of forces and laws of motion, and the goal is to be able to determine the stopping distance of your Hot Wheels car. So let's look at the end result, which is you're going to have a ramp set up with an angle that's going to be an input value and a distance on the ramp that will also be an input value. And then your goal is to tell me how much distance from the end of the ramp will your car stop at. Okay, so this is your output. So now we kind of have it defined what the problem is. We really need to kind of go backwards now and look at what we're going to do in the beginning. So if we look at where we're at in the beginning, we need to figure out like how much friction is your car going to have in it as it goes through. So we are going to examine just this area here to kind of look at the actual data that we're going to collect. So if we kind of look at this situation here, so I'm going to redraw just the ramp, and we're going to take really at this point the angle and the distance here are not going to matter. So these are not needed pieces of information, because what we're really going to do is we're going to focus on looking at what happens when we come off of the ramp. So we're going to set up a photo gate there and a photo gate there. So the goal of the photo gates is to figure out the velocity there at that point, the velocity there at that point, and the time that we're going to spend between those two gates. So if we think like kinematics, we know that we've got an initial velocity, a final velocity, a time, and then what we'll do is figure out the deceleration of our car. So again, this velocity will be bigger, this velocity will be smaller, so we're looking at the acceleration being a negative value. Okay, so this is how we're going to see this as a negative value in probably centimeters per second squared. And so that's what we really want to figure out, is what is our deceleration rate. Now when you set up a spreadsheet to do this, you're probably going to have your time in gate 1 or A, time out, time in, and time out. So this is your gate B, this is your gate A, and then you're going to know like what's your flag length. And then once you have those pieces of information, it'll be easy for you to go through and then figure out your velocity at gate 1 or at gate A, your velocity at gate B, okay, and then figure out your acceleration. Now, how do we tie that into like the coefficient of friction? So if you go back and you think about the forces acting on your car as your car is going on a flat track, we know that you're going to have a force of gravity acting down. You're going to have a force normal acting up. And the only force slowing us down will be our force of friction. So in other words, our force normal equals our force of gravity, and our unbalanced force, or our net force, is equal to our friction force. Now I made that a negative because we're going to assume that the car is moving in the positive direction, and that's going to help us get that negative value in our acceleration. So again, when we do our replacement, it's the mass of the car times the acceleration will be equal to our coefficient of friction times our force normal, And then this is where our force normal is equal to our force of gravity. So we'll be able to see that the mass times the acceleration is equal to negative mu mass times gravity. And here our masses are going to cancel out. So our acceleration is really just negative mu g. So if we want, we can now take that acceleration that we got from all of this data and figure out what our coefficient of friction will be, because a divided by g, okay, make that g a negative, will give us our mu. So our negative acceleration that we'll get divided by the negative of gravity should give us a coefficient of friction. Now what we're looking for is we want this to be a constant value. So in other words, we would like to see this number be relatively the same. Kind of goes along with what we did with the coefficient of, or the mu for your shoe. So that'll be our first goal, is to figure out that. Okay. Now once you have that value, you should then be able to make an adjustment to figuring out the velocity at the end of the ramp. So when we start to look at what happens here, we're now going to say, well, in our first car kind of challenge, the cliff challenge, we always made this mark 80, okay, because we wanted to be consistent. Well, we shouldn't have to worry about that, because that distance is going to just be dependent upon the angle and now the coefficient of friction. So if we think about what happens to our car on the ramp, our force of gravity is going down, okay. Our force normal now is acting at an angle, okay, again, perpendicular to the ramp, and our friction force is going to act against what we're doing. So again, we get a free body diagram for what's happening here on the ramp, which means that if we look at this, we can then set up, again, the two equations that we would get from this. We'll probably need to look at the force of gravity in terms of components. So there's our right angle, there's the angle of the ramp, okay, and so really we're going to get that the force normal is going to be equal to the cosine piece of the force of gravity, so the force of gravity cosine the angle, and that the force of friction, okay, is going to be less than that force of gravity pulling us down the ramp. So in other words, we'll get a net force that'll be equal to the F of G sine the angle minus our force of friction. So if we want, we should be able to figure out the acceleration down the ramp, okay, the mass times acceleration, figure out that acceleration down the ramp once we know what that coefficient of friction is. So again, mass times gravity, sine theta, minus mu times your force normal, okay? And again, our force normal is just going to be this, so it'll be mass times gravity times cosine theta. Masses are in all parts, so they'll cancel out. So again, our acceleration on the ramp is just going to be dependent upon whatever the input angle is and your coefficient of friction. So this will allow us to figure out the acceleration as we start. So initial velocity at this point is going to be 0. We'll be able to figure out how fast are we moving when we get to the end of the ramp based on this acceleration and whatever that input distance is. So that's a kinematic relationship. But then we can, once we know this velocity, it becomes the initial velocity. We know back here at this point we're going to have 0 velocity. And that means that we can then figure out a distance, again, understanding that the relationship for our acceleration is going to be whatever our mu times gravity is going to be. So similar to what we did down here. So you should have a spreadsheet that's going to have some data on it. It's going to calculate some accelerations. That's going to find some coefficients of friction. We'll probably average this. Once we have a good average for this, and it looks to be fairly constant, we can then go through, figure out what the acceleration will be for any given angle and any given input, will allow us to figure out our velocity, and then once we know a velocity there and a velocity there, and we know an acceleration, we should be able to then predict our output distance. And then once you have that all set up on your spreadsheet, we'll turn that in, we'll test it, and see if you can predict your stopping point. Okay, good luck, and if you have questions, we'll just talk about it in class.